Good morning and good afternoon. I'd like to welcome you all to the Windchill Modeler 10 in the SysML 2.0 webinar. Just a few logistics. Today's session will be recorded for replay purposes. If you would like to ask a question, just use the Q&A at the bottom of the screen. I would now like to turn the call over to Patrick Ollerton. Patrick, you can go ahead.
Thank you. Hi, everyone. It's my great excitement and pleasure to be able to talk to you all today about Windchill Modeler 10, the new release of PTC's MBSC tool, and also SysML 2.0. So SysML 2.0 stands for Systems Modeling Language and is a standard published by the OMG. So that's the big set of capabilities that we're delivering in the Modeler 10 release. So we'll talk about both of those two things interchangeably throughout this presentation, throughout this webinar. So we have a 2-hour session planned, quite a lot of topics to cover. We'll do a break halfway through, so about an hour in, we'll take a break. So here's the agenda. I'll just dive straight into it. First of all, we're going to look at a generalized MBSC process. Every customer scenario is slightly different. Every product development scenario is slightly different. But as a generic, generalized MBSC process, this is a pretty good starting point. First of all, you're looking at requirements. Then you're trying to define the scope of the system that's in focus. Then you'd be looking to define the system functions. So what features and functions must be provided by the system. Then the next step will be to define the system architecture, the logical components, structure and hierarchy, and relationships. Then digging into the next level of detail, we'd look to define the system behavior. So really, how does the system operate? What inputs and triggers does it have to change behavior, change states, trigger actions and flows? And also utilize things like expressions and calculations to simulate and calculate behavior. The next step is to do verification of the system design. So this is analysis, reviews, and simulation studies, and then trade-offs to different designs to ensure that the system design meets the requirements. And then generally at the final step, there's some step to propagate the information in the system design model to downstream systems such as CAD and PLM. So this is a good basis upon which to frame the capabilities that we're delivering with Windchill Modeler 10. And as we step through the features, we'll follow this process. This is iterative at each phase of each step of the process, and really at different levels of detail within a product in focus. So we can go through that process at the top level, the system level, then the subsystem, then the component level, and continually iterating and refining the design to truly represent what we want to build. So that's just a quick introduction into the MBSC process. Now let's look at Modeler 10. So this is planned to be released towards the end of August 2023. The software's ready to go, so it's looking in great shape. You can see some of the screenshots there, and we'll obviously see a lot more and some demos during this session. The main focus of the release is SysML 2.0, the next generation systems modeling language. We've implemented the core capabilities, and we'll talk through all of those: function modeling, structure modeling, and OSLC integration. So we've not implemented the full standard, as we'll talk about. We're going to do that incrementally over time. But we focused on the first few phases of that process, the first few steps of the MBSC process, to ensure that our customers and users are able to start MBSC projects using SysML 2.0 as soon as possible. Also in the Modeler 10 release, we've updated the web interface. You can see a graphic at the bottom left there. And that now uses the PTC visual style and color schemes and so on. So this is a really big release for the Modeler team. The SysML standard has been many years in the making. So this is the first of several releases where we deliver these capabilities, and is a real milestone in our industry. As I mentioned, Modeler 10 is the first of several releases that will deliver SysML 2 over time. Modeler 10 continues to work as before, so we'll support all of the existing capabilities and profiles, UML, SysML 1, UAF, code generation, and all of our other capabilities. None of that is affected. SysML 2 is a new solution that we've added on top of everything we already have. So our users can work on their existing models. They're automatically upgraded as part of the upgrade process when you moved from 9.x to 10, and we'll continue that going forward. One question is around migration of SysML v1 models, version 1 models to version 2. And into the future, we'll provide tools to facilitate this migration of models. So let's talk about SysML 2 a little bit. It's an evolution from SysML v1, which was released, I think, 15 years ago or so. And SysML 2 has been in development for, I think, 7 years or so, including all of the requirements gathering from industry, which we were involved in. Hedley Appley was one of the people who submitted requirements for the RFP. And the last few years has been authoring the standard, refining and reviewing and so on. SysML 2 is a language and a meta model for designing and capturing complex systems. It covers these main areas: requirements, behavior, structure, analysis, verification. Views and viewpoints at the bottom are really more the control of the visual representation of the model. It's not actually part of the system design as such. So the actual coverage of SysML 2 is quite similar to SysML 1, but it's been improved in many areas, simplified and expanded in a few areas as well. On the right side of the graphic, you can see the 3 different aspects that are quite new. Certainly the textual notation, the graphical notation we've always had in SysML 1 and is familiar to many of you, I'm sure, and the standard APIs. So the SysML standard expects that a SysML 2 tool will provide these standard APIs, REST and OSLC3. So that makes sense. So it can facilitate data exchange, data sharing, product traceability, and so on. The graphical notation is a visual representation, a graphical representation of the underlying model. So the model is captured in some kind of schema. In Modeler, it's in a database, a SQL Server database at the back end. And the diagrams, the graphical notation is a visual representation of that model. The textual notation at the top is new, and this is a one-to-one mapping with the model. So the textual notation is another way of viewing a model, defining and creating a model. And as you can see, it's kind of like simple code. So this is a big step forward in that it allows system models to really be like an executable programming language. So as you define the structure of the system, the behavior of the system, you're able to actually execute the behavior of the system, perform calculations, and then do analysis on those results. And again, it needs to be a one-to-one mapping with the model definition. So into the future, we'll be able to see tools where we can generate the textual notation from the model definition, create a model from the textual notation, and also potentially share model definitions much more easily using any of these different formats. So there's different training available. You can find some on YouTube from the authors of the standard. I'm building training from PTC. There's this course. So this is really the main starting point for learning Modeler 10 and SysML 2. We have help, an example model, and a few other resources as well that we'll share over time. Here's the official definition of SysML. Certainly most of the MBSC practitioners will have read this before. It's no change to what we had before. It's a general purpose modeling language for modeling systems. and it's intended to help enable a model-based systems engineering approach. So it gives you the ability to create and visualize models that represent many different aspects of a system. With systems modeling, with SysML, we don't necessarily capture the full product or the full system. We focus in on the areas of the system or the product that are most important to confirm the behavior, to confirm the design and the structure. So, as we mentioned before, we have requirements, structure, behavior, and also analysis and verification cases. So there's the testing loop that we can do to feed back into the design and optimize the structure and the behavior of the model based on the analysis and the testing. There's a bit of history. So yeah, 2007 for SysML 1. There's about 6 or 7 main MBSC solutions in the market. It's widely adopted in safety critical complex product development. Again, a bit more history. Here's the RFP. You can access this online. The latest standard documents are available. They've been shared on Git. It's freely available on Git as well, but they're now under the OMG websites too. So you can see the different PDFs that explain the standard. There's some training provided. Okay, so I need to explain that too much. The main goals of SysML 2 really to increase adoption and effectiveness of MBSC. So although MBSC has had success in certain industries over the last 15 years, it hasn't gained widespread adoption in other industries and verticals. So the authors are looking to improve that by increasing the precision and expressiveness of the language. So remove any ambiguity that there was in V1. Ensure the language is more consistent throughout and well integrated. Ensure it's interoperable with other engineering models and tools. That's why we see the API as one example of that. Improve usability by model developers and consumers. So make it a little easier to actually model. Ensure we support extensibility for domain-specific applications. So we need to be able to tailor the SysML meta model for specific domains. And of course, provide a migration path for SysML 1 V users to move those models to V2, which is not without challenges. I'll talk about that in a little more detail later. Some of the key concepts that are used from what's called KernML, kernel modeling language. This is another OMG standard that's kind of a foundational layer for SysML 2. And it provides some of the base meta model entities, such as an element, which is a thing, an item, an object, a relationship. Obviously, that connects two things together to create a basic graph. Dependencies, annotations, information about the model. Concept of namespaces. So we have the concept of ownership through namespaces. So a package, like a folder we know in Windows, owns or contains certain elements, certain items or files. So we have namespaces that are packages and other items that are used to own other elements and organize other elements. We have a lot of OO concepts that are baked into SysML 2. Its heritage is an extension of UML, Unified Modeling Language. So a lot of OO concepts are here, like specialization. So throughout the model, we have the ability to subclassify elements and using subsetting, redefinition, and feature typing. We'll explain all these in a little bit more detail, but they provide mechanisms for reuse and a well-structured design. SysML 2 has expressions as well to define calculations and results. They use constraints and requirements. So this is the part of the language where you can actually define mathematical equations or behavioral equations and maths that define the behavior of the system and then calculate them and execute them and get a result out. SysML adds on top this pattern at the top called definition and usage. So this is a simple kind of template and instance sort of pattern. I'll explain it in more detail in a moment with some examples. But this is one of the main ways that you can define or you can manage reuse within a SysML 2 model. Variability has been added. This is new for SysML 2. It didn't have variability. And we'll talk about that in a little more detail later on. Requirements, still part of SysML. Their behavior and the semantic meaning of them has been enhanced quite a lot. They now behave as a constraint. It's a specialization of the constraint element. And this imposes certain characteristics upon requirements that they're treated as something that must be satisfied for a solution to be valid. Again, we'll see a bit more of that in a second. We include cases, use cases, verification, and analysis cases. Use cases are similar to what we all know and love, that they describe the behavior of a system, the functional features that are delivered by a system or that are required by a system. Analysis allows you to manage and control all of the calculations and different types of simulations that can be run. And verification case is a formal way of tracking how we test, verify the model, the design against specific requirements. Other areas that kind of fundamental, attributes and enumerations, so we can model all types of characteristics of the system entities. Enumerations, so we can have lists of values. The main types of entities that we model with, sort of the main, most common things are listed below. Items, and these are elements or entities that are used by a system. Something like fuel, for example, some kind of consumable. Part elements are the foundational units of a system structure. So as we'll look for the throughout this webinar, we'll be looking at parts and part structure modeling a lot. The structures can be decomposed, interconnected, form composite parts, and together form a system. Ports are connection points that enable interaction between parts. Connections and interfaces are how we communicate or connect to those separate elements. Allocations assign responsibility for realizing the features. So I think a lot of these notions and concepts are familiar and no great deviation from what we've used before with SysML 2. Other things that are probably new, occurrences, individuals. This allows you to manage individual life instances, time-based instances of systems models. So they have temporal and spatial extent, potentially, and they have a lifespan over time that you can model and track. Elements of behavior that I've talked about briefly, actions that show the different sequence of events or messages that occur within a system when it's performing functions. The states show the valid transitions between the operating states or the system states of the model. Mentioned calculations and constraints already. And briefly, viewpoints. Viewpoints and views allow you to configure how you view the underlying SysML 2 model. So for example, you could say, I want to see this set of parts in a package in a table. That'd be a pretty simple view. More likely you'd want to see it in some kind of graph or network diagram. So viewpoints and views give you a way to control that and actually configure how you see the information graphically. Finally, at the bottom, metadata there. This is simple tagging type of capability. So you can put, whatever kind of textual sort of language information you want in there. I mentioned that CoreML is one of the foundational elements of SysML 2. It's not something that we're going to dive into in any real detail. It's really just provides some of the core elements that surface in SysML 2. Namespaces, I've described those briefly. They denote the scope of owned elements. We see some examples here. In this example, we have a package A that contains package B, which contains a part definition called vehicle. And we can reference that using this kind of notation with the semicolons. And you see that kind of feature chaining. So you're able to address specific elements using effectively the fully qualified path to that entity. And here's definition and usage, and it's a reuse mechanism. So pretty much all of the elements in SysML 2, you can create a definition version or a usage version. The definition is there to act as a template. When you create usages, you can say, okay, this usage is typed by this definition. And what that means is that usage will inherit the features the definition has. So if the definition has parts, attributes, behavior, then when you create the usage from it, it will inherit all of that as well. Obviously, if you're creating multiple elements that are similar, it makes sense to kind of push any common features into a definition so you can easily reuse. And some of the other mechanisms in SysML 2 allow you to reuse and kind of override or redefine the features that you've inherited. Graphically, it looks like this. Definitions have square corners. The usages have rounded corners. So we'll see this in Modeler in a second. Okay, so when we look into Modeler and create a new model, we have a new choice in the list of model types, SysML 2.0. It utilizes some of the capabilities or behavior of SysML 1, some of the logic and code in Modeler in the background. So that also gets selected. So that's pretty straightforward. We've extended the package browser so it can now display SysML 2 elements, and the behavior has been enhanced as well. So for example, we now see relationships more commonly. Pretty much most of the relationship elements in SysML 2 are now visible in the package browser, which makes it easier for the users to see those relationships and manage them. So we can see packages in a package hierarchy, and we have a different icon to denote SysML 2 packages distinct from standard packages. We can see some requirements in here, some use cases, some parts and a part structure, some annotations, some system structure diagrams, and then some variability entities. Creating packages is straightforward. You can create a standard package in the normal way. It's one of the first actions on the context menu. We have this new package type for SysML 2. So to create SysML 2 elements, they need to be inside a SysML 2 package. One of the features of SysML 2 is importing. And for those that are familiar with programming, then it's come from that idea, the ability to reference other parts of SysML that might be in SysML files and import in the definitions or the usages or features of other types of the model. So we're still working out exactly how we want this to work within Modeler. We can create import elements and we can specify the element that you're importing, but we still haven't sort of fully finished how we're going to implement this. And you'll see a few examples throughout this presentation that we haven't fully implemented some capabilities at this point. We'll be looking to do that into future releases, of course. So at the moment, this is a representation of the import concept. So we will complete the implementation and provide the kind of useful capabilities. In the textual format, it gives you the ability to access elements that are outside of the scope you're working in. When we're using Windchill Modeler, we don't have those kind of restrictions. When you're in a model, you can access, as long as you have the access permissions, you can access other parts of the model easily. So we're not sure what real benefit this would really give to the users, but we're still working on that. This is how you create it. So using the context menu, you can create a new import and then specify what you're importing, or you can use drag and drop. We've implemented a lot of drag and drop features for SysML 2 to make a lot of operations more easy and more intuitive and faster. We have SysML 2 has an alias element. So this allows you to provide alternative names for elements that can be used in different contexts. And you can have as many aliases as you wish. Again, in Modeler 10, it has quite limited functionality. We can apply the alias. But again, it's more of a programming language notion that's beneficial for the textual format. Instead of having to use the fully qualified name, like we see in the graphic here, to reference an item, we can use aliases to reference them with a short name. So if we were writing some code in a different package, we could import this, give it an alias, and then reference it with an easy name. So again, we're working out how this can offer benefits to a modeling tool like Windchill Modeler. We're providing a reference model. So using the generic process that we see a graphic here, we've got an example or a sample model that customers can use to start modeling with SysML 2. Has some packages set up, some diagrams and elements. It'll be on PTC support, the PTC community. There's a text document that you can see that shows the process. And over time, we'll enhance this and add more definitions to it to help our users, our customers, get a quick jump start on SysML 2 projects. We also have an example model that's version 2 of HSUV, which is famous in the MBSC world. And this illustrates a lot of the elements that we've implemented in Modeler 10. It also illustrates a lot of the concepts in SysML 2. You can see at the bottom here, example of definitions of feature typing, subclassification. And over time, we'll provide links to training and guidance, so users are able to take the example model, look at a generalized process, understand the steps, then understand the features and functions in Modeler that support that process, and then look at these examples to see exactly how you put things together in real life. Again, this is something that will continue to enhance over the next few releases as we add more capabilities. We'll build out this model with things like behavior and calculations. Okay, so here is a quick demonstration of that model template. So it sets up all of these packages that align with that process and the steps. Here's the text document that you can refer to. And this content, this training will be provided as well. We'll end up putting it on YouTube, most likely, so it'll be free for customers to use. So we have some requirements set up, some diagrams with a starter requirement, use case diagram with a starting use case, a simple example of a system part structure and a decomposition. we open the diagram, we can just see some subparts, attributes, some ports, a connector, and the feature typing relationship to the part definition. So users can rename these entities and use this as a simple starting point to help accelerate adoption. Okay, so let's look at a bit more specific features and capabilities. System requirements. I mentioned that they're treated as a constraint. It's a specialization of the constraint element. So these impose those constraints that the design solution must satisfy to be considered valid. So these constraints might be text statements, like the system shell, or an expression. So it relies on some kind of mathematical equation. Something simple may be total mass for a given product or system, or fuel consumption, fuel efficiency, emissions, whatever kind of design targets that you have in place for the product should be expressed through your requirements, and then they should drive the analysis and the calculations. They should have a subject. So which model element is this requirement attaining to? And these get treated as parameters. So really it's seen as an input to this requirement that can then be tested using those constraints. It may have actors and stakeholders, and it can be resolved to true or false based on the state of their constraints. They can be decomposed and nested, so you can build up structures of requirements. So requirements in SysML 1 were quite simple. We can see that they've got a lot more capability, behavior, and logic behind them now, which gives us the ability to do a lot more advanced analysis and verification downstream. In the tool, in Modeler 10, this is how we create them. We can create them from the toolbar on a system structure diagram. We can create them using the context menu, as you see on the right there. And you'll note that we're creating a usage in this example, rounded corners, and we've created it here. The definition elements are away on the right side of the toolbar. And you'll use these when you're kind of working in more template and meta modeling kind of mode, I would say. The actual design instances, the systems models, is primarily usages connected together that are based on definitions. So we can create the decomposition. We can relate requirements to each other. In this example, we've got some requirements that are linked via OSLC to CodeBeamer requirements. These are OSLC surrogates. So it's a model item, but really it's an external item in CodeBeamer that we've represented here. We can also use drag and drop to create nested decomposition of requirements. So you can move them around here to determine the hierarchy. And then you can populate the diagram. So if you make changes in this window, they're not always reflected automatically in this window on the diagram. So if you populate, you'll then see any changes that you've made to the hierarchy. Oh, I should have mentioned before I jump on. And as with standard modeler behavior, when you select an element either on the diagram or in the browser on the left, the properties panel is displayed at the bottom right here. So for all of the SysML 2 elements, we have new properties, new values, and they're all accessed through this properties page. Jumping ahead a little bit, but we can define and capture requirements traceability. The SysML 2 element is called satisfy requirement. It's an element that acts as a link. So we can drag it from a model element, a part in this case, and then point to the requirement that it satisfies. So we can also use other relationships between requirements and model elements, allocation, connection, dependency, depending on what you're trying to represent and describe and capture. We can also create SysML 1 requirements in a SysML 2 model. Now, this is something that we may not continue into the future, but for the moment, we think that having the flexibility of allowing SysML 1 elements and SysML 2 elements to live in the same model will be useful. One of the main reasons that it will be useful, it will allow our customers and our users a more controlled path for migration of models. So rather than having a hard cutover from 1 to 2 at some point, or a migration effort in between, we think it might be sensible to allow SysML 1 and SysML 2 to coexist. Now, of course, there are caveats to that. You have to be very careful about how you do that. But maybe one good approach would be that if you have SysML 1 elements, you can bring them forward, but new designs or changes to that design do in SysML 2, so that then over time, the model becomes a higher percentage of SysML 2 elements compared to SysML 1. So we can link to SysML 2 elements. So we can link a SysML 1 requirement to SysML 2 elements. So there is that traceability. It's pretty limited though. So it's probably have to be cautious, have to suggest caution if you're considering this approach. But allowing to bring forward your requirements from SysML 1 and then use them as you build out the rest of the model in SysML 2, the use cases, the parts, and so on, I think is advantageous. It means you can reuse your existing requirement set in a new model. Okay, so that's requirements. There's a lot more detail. I didn't go through a lot of the properties for those requirement elements in detail, and we haven't implemented all of what is expected in the standard. Because we haven't implemented something called the calculations and the expressions part yet, that's fundamental to the requirements. So we can't really finish requirements until we've got some of the other fundamental elements done. So there'll be more behavior that's surfaced through the user interface and through the capabilities over time in future releases. And the same applies for the next section, system functions. So this is a set of cases, which is a calculation that produces a result. So it's like some analysis or a verification test kind of thing. There's some sort of input, a subject. Again, this is treated as a parameter. So if it's a part or if it's an action, which is a function of behavior, that is treated as the input. Or it could be an attribute that's a result of an element, on an element that's the result of a calculation. So the cases have objectives and actors. And this is the generic elements. The users will be using a use case elements, and it specifies the required behavior of its subject. So again, has a subject, objective, can have actors, which are also parameters. So they can be seen as inputs to any kind of calculation that's behind these use cases. Now, use cases can be decomposed, they can be nested as well, as we see in the graphic there. The way I've understood SysML 2 is their intent is slightly different to use cases as we've seen them in SysML 1 and UML. It's a little bit more focused on what the system will provide that we can test. Whereas I believe SysML, UML was use cases were originally intended to be more of an external viewpoint from the stakeholder's perspective. What functions does the stakeholder want to have delivered in the product or the system? So I think there may be some change slightly in how these are are intended to be used. But that doesn't limit us to using them as we had before. Through the UI, we can create them again through the toolbar on a system structure diagram. Directly in a package using the context menu, we can create the use case usage or use case definition. We can create decompositions graphically like so. We create these by clicking inside symbols when we create items. Here we can see a relationship from a use case to a requirement. The properties panel, we can see. We can use drag and drop to manage the hierarchy as with requirements. And you'll see that there's a lot of consistency in the capabilities for modeling. The graphical notation, there's a lot of consistency across the different elements. And the way that we create relationships and create elements is consistent with SysML 2 and in Modeler 10. With use cases, we can define subjects and actors. So this is what we mentioned a moment ago, where we have another model element that acts as the subject. And in this case, it's the power subsystem part. And it can be visualized and seen on the diagram itself as well. The other part here is a stakeholder, another model element that's involved in some way. And these can be treated as parameters. On the right, we see a part called driver that's performing the role of an actor. So these are all three parts, but this part is a special type of part that is performing the role of an actor for this use case. So like we saw with requirements, we are allowing SysML 1 use cases inside a SysML 2 model. So again, there's limited capability. It's really only coexisting. You can link them to SysML 2 elements, so there's basic traceability there. But it does mean you can reuse use cases from SysML 1 models, and then start to build out the rest of the system or make changes using SysML 2 onwards. Okay, so the bulk of the presentation is really in this chapter, modeling system structure. We feel that this is really the most valuable aspect of SysML 2 in those early phases. As we know, PTC has market-leading requirements management tools in CodeBeamer and Windchill RVNS. So Modeler isn't really intending to be a heavyweight requirements management solution. We have our OSLC integrations that allow us to create links or surrogates to external requirements in CodeBeamer and on RVNS and third-party tools as well. So we'll be implementing what's required for the SysML standard, but of course, recognizing that a lot of our customers will really be using OSLC to connect system models to upstream requirements in other systems. So really the big area that we've focused on is this logical structure modeling. Let's talk about this in a bit more detail. So a few slides just to give a basic overview. The part entity, the part element in SysML 2 is the modular unit of structure. So what are the things that your system is made up of? And it could be physical things, it could be digital things as well. So you can use and apply this to multidisciplinary design. It doesn't have to be hardware, it can be software, electrical design. This is an abstract representation of a product of a system. So it can represent whatever is of interest and requires modeling, analysis, and optimization. So it could be part of the system, a component of the system, or an external entity. So like we saw a moment ago, it could represent an actor in a use case or a stakeholder. could be used as an input potentially if it's some kind of material. It could represent the environment in which the system operates. If that has an influence on the behavior, then it could also represent that as well. If it has some interaction with the system, then it can be captured using parts. Parts have features, so they can have attributes to describe their characteristics, ports, connectors, actions, which describe functions they can perform. They can inherit features, and one of the ways is that feature typing. If a part is typed by the definition, it will inherit that definition's features. It can be decomposed, and we see these smaller symbols, contained owned members, decomposed parts that are owned by the parent part or the higher level part. Graphically, and we see this in Modeler. At the top, there's an identity compartment. Then there's sort of a compartment stack for properties, and then a graphical area where we can see what's inside this part and any relationships that it has. Ports allow you to define a structured interface, so a standardized defined interface that controls interaction between parts. So if there's some mechanism by which these are communicating, maybe it's an electrical signal, maybe it's software code, maybe it's some kind of fuel or consumable that's being transferred from one element to another, then you can control and specify how that should occur. The connection is the actual link between these elements, either port to port or just feature to feature. And then they can connect externally. So any other parts that are not part of this structure, we can define relationships to those as well. So we can see all of this in our package browser. We've already seen some examples of this. We see different elements and links. We look on the right here, we can see at the top some definition items. They have a D in front of them to denote that. They have square corners. And then we actually have a part usage and a decomposition. Now we can see the name of it. It has a name and then vehicle. Vehicle is its definition. So vehicle is defined up here. It has certain characteristics and features. Hybrid SUV is a usage of it, and it inherits features. It defines some of its own features. It has some more parts, some ports, some connections, and so on. So all pretty straightforward and logical so far. In Modeler 10, the main diagram type is called System Structure Diagram. Into the future, we'll provide more specialized diagram types for different types of modeling, but today we have system structure. You have to create it inside a SysML 2 package, as I mentioned earlier. And then we are able to use the toolbar to create any of the main structural modeling elements. And we can click on the item and then click in the canvas into space or on a symbol to create new elements and add them to the diagram in one operation. In the example we see here, we've got a part usage. Here's the hybrid SUV again, and we see the feature typing relationship with the parts, with the vehicle part definition. This has an attribute, CO2 emissions, so the hybrid SUV will inherit that attribute. So a really simple example just to illustrate the concept, what's going on here. And of course, for those familiar with OO, this is all pretty standard stuff. There's an example of a requirement linked on the diagram here. There's another part definition here that should be connected to the battery pack. We see some ports, and we also see nested ports. So as well as sort of nesting and containing parts, ports can be nested inside each other as well. As well as using the toolbar to create new elements, you can drag existing elements from the package browser and drop them onto the canvas. So it's quite flexible in how you model. You can use different ways to create elements. Here's the context menu. Don't really need to explain that. You've seen examples of here. Here's an example of decomposing into subsystems. So in this example, we have an existing part. We've clicked on the toolbar and then clicked inside this symbol. This will then create a nested part, an owned member part. And you can see that we've got the same name. You probably wouldn't want that. But just as a simple example, that's one of the ways that you can create that nesting. Or you can use drag and drop. So you can drag the child, the sub part, onto the parent, the higher level part. And you see this pop-up menu. So you can create a copy, or you can move it. So it then becomes an owned member. And then some other functions. We can create a subsetted item, a redefinition of an item, or build a relationship between the existing items. So we'll talk about this in a little bit more in a bit of time. This is kind of creating in context with drag and drop. In this example, we're dragging a definition from the package browser onto a usage. And we can create a new usage here. So that'll create a new element that's typed by part definition 1. Or we could just choose define by, and it'll build that feature typing relationship with this usage. So once we've done that, then we can run the populate, and it'll show it on the diagram. So just an example of how we can use drag and drop to perform lots of different modeling tasks, whether it's creating relationships, creating new items in context. So we end up with diagrams that look like this. In this example, we've got an attribute that's contained within a part. We've got an item element. And as I mentioned, this is something that can be used by the system, something like fuel potentially, or some kind of consumable. If it has an interaction with the system, then you'd want to model it. Interestingly, SysML doesn't really impose many restrictions on what elements can own other elements. So, it gives you the ability to make system models that probably wouldn't be logical. So over time, we will be imposing restrictions and probably allow the user to determine what is allowable in terms of what can own other elements. For example, a requirement can own an attribute, a requirement could own a port, for example, and then that port could own a part or a use case. So that may not really make sense. It gives a lot of flexibility, but it means the modeler, the user, needs to make intelligent choices, of course. But I think some way of constraining this makes sense. Another feature of SysML 2 is reference parts. So this is where you want to include a part in your decomposition, in your structure, but it actually belongs to another decomposition or another structure. So this is realized as a reference part, and graphically it's shown with a dashed line. We haven't fully implemented this yet in Modeler 10. We can define reference parts, but we need to hook it up to the reference that it's linked and connected to. So it's only half implemented at this point. Creating ports, again, using the toolbar. And you see graphically, this is quite interesting. A port is a circle, and the port definition is a square box. So this is a feature typing relationship. Port 1 is defined by port definition 1. It inherits all of the features, so we can standardize and reuse a lot of our models. More typically, though, we'll see the port actually in place on a part structure like so. Again, like I mentioned, really, when you're working with definitions, that's really kind of meta modeling. You're defining the sets of things that you're going to create and what features, characteristics they have. And then the systems engineers will be using usages defined by those definitions. Okay, that's all straightforward. One of the things about ports is they have direction. Certain SysML features are what's called directed, so they can have a direction in, out, or both. And we can see that on ports. We can see the property on the graphic there. We set the direction to in, and we see it graphically on the port itself on the diagram, pointing in or out, or both ways, both directions. Something that we've not fully implemented again is port conjugation. And this is the principle that when you define a port, if you choose it to be conjugated, you should have a corresponding matching port with the opposite direction. So if your port goes out, you want a port on the other side that you're connecting to take an in direction. So we've implemented the foundational meta model and some of the capabilities. As you can see here, we can set a port to be conjugated. What we need to do is have the matching pair with the other ports, and then keep those in sync and inform the user of these relationships. So more to come in the future there. One of our utilities in Modeler is called the creator or item creator. And this allows us to create multiple items in one go. A lot of what you've seen so far is creating one item, then one item. This allows you to create multiple diagrams, multiple elements in one operation. So you can filter what you choose from. This is a list of valid elements based on what package you have selected. So here we see all of the SysML 2 elements. So if you need to go through and create 10 parts, 10 attributes, whatever, you can do it very quickly and easily here. So yeah, it's really more of a multi-object creator and a nicer experience as well, certainly than the context menu. The toolbar is a great way to model. The context menu can be a little hard work, a bit clicky at times. So this is I strongly recommend this is a nice way to create models quickly. Okay, so here's a demonstration, and you can see by the time at the bottom there, I did this today with the very latest build. So we're starting off from that process that we saw at the start. We're looking at defining the system architecture. So I've created a new package just for the demonstration. I'm going to work on a new subsystem. So we'll create now a system structure diagram, allowing us to add those SysML 2 entities and elements. So we'll create a part using the toolbar at the top. We can type in the name. I'll create another part, and I'm going to create this as a decomposition. So I've clicked on top of that symbol. This is now contained by subsystem A. Expand the symbol out, so I've got some room to work. So I've renamed this and a little typo, then I correct. Okay, and we can reposition easily using drag and drop. Okay, so I'll put in another part. This second one's an owned member. And then another one that's an external part, so not part of this subsystem, but has some interaction with it. So let's build some relationships. So first of all, we'll build a simple connection. So this doesn't need ports. This is a lightweight, simple connection between two model elements. In this case, two parts. If we want to have a more structured, formalized interface between entities, then we should use ports and type our interaction. And in this case, we can use connections or interfaces. Interfaces must connect through ports. They're more formalized. So because we're connecting with an external entity, we're using a standardized sort of protocol for our port. Here we've got some existing requirements. These are the example ones that are in the starter template model. So I've dragged a requirement on to the diagram, and now we can create the SysML 2 relationship for satisfy and drag a line from the subsystem A to that requirement. We can see all of those relationships and entities in the browser. So if we expand those elements, we'll see the ports and the relationships. And it's much more clear than SysML 1, certainly how we've implemented with Modeler, be able to see those relationships, see those, what is the connected item on the end of those relationships as well. So we've seen quite a few examples of creating models using diagrams. This is, in the graphic, you can see how we can create some of those key relationships for SysML 2. Feature typing, subclassification, subsetting, redefinitions, and reference subsetting. So feature typing is this definition and usage relationship. And we can see how it looks on a diagram from the definition. The relationship points from the usage to the definition, meaning that the usage is typed by that definition and inherits its features. One important thing to note is a usage can be typed by multiple definitions, so it can inherit multiple sets of features from different elements. This is the example that we showed earlier, the HSUV typed by the vehicle definition. You can see all of the inherited items in the package browser. So in the parts browser, the package browser shows containment and ownership. The parts browser will show you all of the elements that have been inherited from definitions and other relationships. So you can see some in the graphic on the right here. Inherited features have the caret symbol before them. You can manage the relationship on the properties page. You can see the relationship that's specified from the usage. We have a reference object. So below that part, you can see that there's a feature typing element or entity that describes that relationship. So you can go and change it if you need to in time. I mentioned earlier that they also have the D prefix in the package browser. Here's an example of using definitions. So we've set up 3 definitions to categorize parts, system, subsystem, and component. And we can specify specific features for each of those definitions. And then in our actual hybrid SUV, we can apply that definition to the different entities in the system. And this gives us a basic sort of taxonomy classification mechanism. Here's an example of using drag and drop to create that same feature typing relationship. So I drag a port definition onto a port in the package browser and choose define by. Do the same thing in the underlying model. Here we're dragging a definition onto a diagram, onto a usage. Again, we can create the define by feature typing relationship. We can also use the favorites panel, this little pane here. We can add entities to there and then use them for drag and drop. In case we don't know where they are in the package structure, sometimes package structures are large, so you can't find the right item. You can put things in your favorites and then use them later for creating these relationships. Subsetting allows you to further specialize an element's definition. So in this example, we see that we have an engine definition with multiplicity of cylinders between 4 and 8. then we can specialize that and have a 4-cylinder engine and subset each of those features so we can uniquely address each one. So you see that we have cylinder 1, 2, 3, 4, and then we can treat each one as an individual entity on its own. This is how we create a subsetting relationship graphically on a diagram. We can do the same using drag and drop. So I've dragged the base usage with 4 to 8 multiplicity onto the rear left wheel, and then set this up as a subsetted item from the wheels item. If we want to create a new element as a subsetted item, we can do that as well. The last example, there was an existing item and we're building that relationship. Here we're creating a new item. So creating in context is another example of that. Redefinition is conceptually like overriding something that you've inherited. So it provides a way of reusing features and element entities and then specifying and redefining them so they match the need, the usage that you have. Here's how we create a redefinition. So part 1 is a redefinition of part 2. It inherits its features and can override them. Think of an example, if it inherits an attribute value, you can then override that value in part 1. Again, we can use drag and drop. We can create a relationship between an existing entity and a redefined electric motor in this case. Or we can create a new element in context as a redefinition of an existing usage. So all of these ways of modeling gives the user options. It allows them to work in an intuitive way with drag and drop. It's very quick, able to model very, very fast. The other type of relationship we have is specialization, subclassification. So this is primarily for when you're working with definitions and you want to build up a taxonomy of entities, of templates effectively. So we have a top level item vehicle, and then we have some specializations subclassified from it, a hybrid truck, and then a full electric vehicle. So these inherit some of the entities defined by the parent ancestor class, and then have some of their own features defined as well. And then at the bottom, we have some usages that are obviously instances of these subclassified definitions. So this is a really good way of building up reuse, building up modularity in your designs. Defining attributes, so key characteristics that you want to model and capture, and then downstream use for calculations and analysis and so on. We can define these again in the same ways using the toolbar on system structure diagrams. So here we can see we have a part definition with an attribute defined in there. This attribute is defined by a definition that specifies the unit, the quantity. We can specify properties for the attributes. Primarily, the most important one is the value. So we can assign the value to that attribute usage, mass in this case. We can define enumerations, not fully implemented in Modeler 10, but this allows us to define a discrete set of valid values for an attribute. Another important feature of SysML 2 are the model libraries. And these are a set of standard definitions for engineering constructs, such as standardized units and quantities. So there's a big list of standard units defined by IS and ISQ standards bodies for defining these types of engineering constructs. Other things such as analysis, engineering, equations and calculations, spatial models. So there's some basic kind of geometry that can be used. And then base definitions for SysML 2 elements. So each of the elements we see in like part and use case, they all have a default definition that's being used in the background. So all of these are provided with the standard, and they are in .sysml format. So this is the textual format. You can see examples of that. And these can be imported into a SysML tool and reused. We have an importer tool that isn't fully available or ready for customer use at this point. Into the future, we may have a tool where we can import these and kind of manage that process. For now, and it may become our longer term solution, we've put all of these library files into component sharing wizard modules, and they can then be imported and used in models in Windchill Modeler. So first of all, we create a library package. So this will create a load of SysML 2 elements. So they get brought in as attributes with definitions and so on. So they need to be in a special package so that we can handle them in a certain way, because it's not part of our model. It's something that we're referencing from a standard set of model definitions. So we use component sharing. We import the file. You can't see it too well in the graphic, but in this example, we've imported a load of a lot of attributes, ISQ base properties. You'll see some things like length and mass down there. And these are obviously fundamental elements needed to be able to perform lots of engineering. So looking forward, as we want to be able to do analysis and calculations, being able to reference all of these standard attributes and equations is very important. So this is a really easy way of doing that. You just go and select the file, import it, and you can then reference those standard attributes in your models. So here's an example in our hybrid SUV. I've created a new attribute called drag coefficient, and it's typed by a standard attribute called drag coefficient value. It's actually been inherited from vehicle definition, and we see that what we've inherited are quite a few different ways of managing and manipulating that property. So these are quite complex definitions, but they're defined in a way that you can actually be usable downstream in calculations and so on, and also enable you to do things like conversions of units, as an example. So I think, yep, here's this example. There's a drag coefficient that I've imported from a mechanical equations and units library. We're then referencing that in our existing definition, and then we can set the attribute value within our specific design. A lot of these model libraries have dependencies, and if you don't import all those dependencies, you'll see some of these stubs. So that's important to be aware. If you import all of those library files, you'll create an enormous model. So one of the challenges there is to be able to not import everything, only import the things that you need. And sometimes dependencies might not be in place. So this will allow you to see those and then go and import the relevant file that's missing if needed. Standard modeler capability that we've realized for SysML 2, show and hide compartments, allowing you to control which properties, which features are shown graphically. So here we see a list of attribute definitions, parts, part defs, and we can see lots of the different properties and features for SysML 2 there. We can select individual elements in this list. And if you see, I've right-clicked on that nested part, and I can then perform some actions on it. So these are actual element references in the diagram here. Here's how we specify multiplicity on the properties page for that element. That's what I did for the wheels part that we saw a moment ago. Individuals, we haven't fully implemented yet. So as you can see, there's a bit of a gap early in the training on here. But we have the ability to set a part definition as an individual. We need to continue the implementation to have the life cycle modeling capabilities needed for individuals. We've seen some of this already. Those key relationships, feature typing, specialized, subset, redefines, they have a standard notation that you see in the textual format. We've brought that into the modeling tool environment so that we have a kind of clear correlation between the notation that people are familiar with, will become familiar with, the textual format, and how we represent relationships in Modeler. So it's very clear to see when we have these kind of key relationships, if something's defined by or a redefinition. And as I mentioned earlier, we can manage those relationships. For this hybrid SUV part, we see a reference object. So this is a pointer to that definition that's typing it. And as I mentioned, you can change this, remove it if needed. You can also go to the reference objects. There's a quick jump. From a usage, you can then jump to the definition of that item. There are some type of special relationships called flows. This is really where the intent is that there's some kind of transfer of information or status between connected elements. So from the toolbar, we have the drop-down menu here that allows us to create connections, allocations, interfaces, and the satisfy requirement that we saw earlier. On the diagram below, we can see that we have some connections, and in the example in a moment, we have some interfaces as well. So here's a connection link. Now, flows can be represented as lines or boxes, and that's because the standard says it should, but you can't have a box connecting two boxes. So we need to be able to define compartments and properties and features on a link. But then we also need them to be able to connect two symbols together. So really, these two are the same things in this diagram here. There's the link symbol and there's the corresponding box symbol, and you can populate one from the other. So this aligns with the standard, and it shows how you can view parts of the model in more than one way. Here's an example of a dependency between a use case and a part. It's a contract between a client and a supplier. So obviously, as we know dependencies in all of our products, that's a strong relationship that has implications if either end changes. Okay, here's an example of a connection. And this is quite a generic type of relationship. It can be used to model lots of different types of things. And you don't need to use ports. It doesn't have any special behavior. Allocation indicates more of a responsibility. So you might allocate some requirements or some use cases to parts of the design, and with the expectation that those parts of the design would realize, implement, and satisfy into the future those requirements or use cases. So it can be used to give you a mapping across different structures and hierarchies of a model. So understanding those sort of high-level relationships on traceability. Here's an interface example. Can only be created between ports because it's a structured connection, some kind of protocol that we can define and reuse, and others can as well. Again, we can create through the toolbar. We can also create through the context menu as well. Here's a nice pattern, or a recommended pattern for defining interface definitions. So we have two port definitions defined. We have an interface definition between them, and there's the connection box, the box version of the link. In our actual model, we have two part usages. They have ports. Those ports are typed by those definitions. So what that indicates is that, you know, these ports are an instance of these definitions, so that a valid interface between those port usages should really only be interface definition 1. So we've created an interface and then made that interface typed by the interface definition. So this is a good way of modeling a good pattern, and again, it aligns with the SysML 2 standard. The relationship we saw earlier between a requirement and a model element to indicate that the design, that the requirement has been realized by that part of the design. We can see these linked elements through the properties page. So as well as seeing the reference objects, we can see more of these flow relationships through these linked objects, link ends, and SysML 2 link options in the drop down here. So nice and easy to see all of these relationships. Here's an example of creating in context. So I'm dragging a definition item from my favorites pane onto a part, and I'm going to create a new usage here. I can give it a name. So this is creating a new part usage and then adding it to this part in a decomposition. Really nice way to model. Same kind of approach, but instead of creating a new usage, we're creating a new usage that's a redefinition here. Displaying elements in graphical compartment. So we see how we have at the bottom, we can display these elements in here. So we can use drop symbol in here. We're still working on this behavior, so I think that in fact it doesn't become an owning element, it's just on the symbol but not an owned feature. But we're planning to change that behavior, so this is not correct for 10, I don't believe, but it will be in 10.1. Here's an example of populate. So we've dragged a part onto a diagram and we're populating all of the existing nodes. And something we'll be looking to improve is the kind of layout of the items that get populated here. So it's a little bit easier to then change as you want them to be laid out. Here we can see another example of populating related elements. So I'd like to see the different feature typings of my part, and then the vehicle is automatically put onto the diagram. Here's an example of the parts browser. We saw one briefly earlier. And essentially this shows all of the contents of a design of a system element, including all of the inherited elements. So this shows you the big picture of everything that's in there. We can define abstract elements, and these are intended in standard MO to not really be used as an actual element in the model, but more as a high level meta definition that can then be specialized further and reused. Okay, so that's the bulk of the presentation. And really that's the bulk of the SysML 2 capabilities. So there's a lot more that we have in the product, but I think that's enough level of detail really at this point. We'll talk about some of the remaining capabilities that's more standard modeler features. So one of the SysML 2 capabilities is these annotations. So comments or documentation or textual representation. Comments are really information about the model. It's not part of the design. It's really more about the model and the development and the reviews, analysis, whatever. Documentation is a special type of comment that should be seen as part of the design. So it's sort of important information maybe on how the system should be used or behaves. Textual representation is there to allow you to input any system code that you may want to include in the model, maybe just some sort of skeleton code to indicate behavior. Have a demonstration, very quick movie demonstration of creating those annotation elements. Again, these are standard SysML 2 elements. So we can add them to a diagram, type in the comment text. This is a review comment in this example. And then we can link to the model element using the annotation link. Let's create a documentation element. So the documentation element it would kind of travel with the model. If you did an export of the model, it would be included in the model definitions, whereas the comments are something that you probably want to strip out. Really, it's not fundamental information. Here's a textual representation. So any type of technical information or code can go into here. Again, let's link it to the model element to complete the modeling. We can look at the properties for those elements and then make any changes that we need to. We can find those in the package browser as well. So we can, as with the other elements, we can see them in the package browser. Okay, a utility that we've added to help users filter and streamline what they see is package filters. So it allows you to hide specific types of entities. If you're only interested in requirements, you can create a filter and then hide everything else. It's really simple and easy to use. Choose the package. And we see in this one, we've got some packages, we've got an import, we've got an alias, and some diagrams as well. So maybe I'm only interested in the structure model. So I'm going to create a new filter to kind of hide everything else. There's already one there already for requirements, but I'm going to create a new filter just to show structure elements. And now we can choose what we want to see. I'm going to clear everything first and then just choose attributes, ports, and parts. I'll even hide other packages. So I'm just going to focus in on this one particular part and decomposition. Choose apply, and we see that everything else has disappeared. And we can just now focus in on that specific element and its structure. If you want to get rid of it, you can just come here and choose clear filter, and then everything's visible again. So really simple and easy. You can propagate those filters to sub packages as well. So yeah, you can really provide a nice, easy way to view the information using package filters. We have variability capabilities in Modeler. So we are continuing to use our existing variability. We've applied it to SysML 2. So orthogonal variability modeling, the standard OVM that it's based upon, continues to work as before. So these tried and trusted modeler features, a lot of customers are very happy with our variability. So we continue to use that with SysML 2. In the future, we need to decide how to reconcile or map our variability to the variability in SysML 2.0. So that's still to be determined, but at the moment we have good variability capabilities. It's not 100% aligned with SysML 2. That will be coming in the future. One thing that we definitely want our customers to be able to do is to be able to do software and system development at the same time. So we are allowing UML elements to be created within a SysML 2 model. So as we can see some examples here, we have some UML elements at the bottom, some classes and a class diagram. It's important to be able to do any kind of model-based software development in the same model as the systems development, so that you can build that traceability and understand the integrations, the interfaces, the proper capabilities, do proper simulation that maybe includes some of that code. So this is another important feature, I think, that allowing our customers to use SysML 2 and UML simultaneously to give integrated systems and software development. For model management, it all works as before. So all of the standard capabilities like protection, versioning, private sandboxes, rebasing, and so on, export, import, they all work fine with SysML 2 models, work just as before. Reviewer today can be configured to perform some basic checks on SysML 2. In the future, we're going to include specific SysML 2 reviews that you can use to test the correctness of the model. So that'll be coming into the future. One thing we have today is our diagram filtering capability. Similar to the package filtering that we had, this provides a way to control what you see on a diagram. Some diagrams are very complex with a lot of symbols on them, and it's difficult to understand or read and difficult to explain to others. So diagram filtering allows you to hide certain elements based on some criteria. And it's very powerful, in fact, that you can put in quite simple criteria like just hide requirements or hide comments, or quite complex criteria based on a property value or something like that, or a relationship. So it's a powerful tool, but it also has a quite simple way of using it if you just want to hide a type of element. And it allows you to really simplify the diagrams specific to the users. It may be that you only need this type of filter for a meeting to be able to explain some parts of the design and the model. But if it allows the audience to focus in, then it's very helpful. And we have hide altogether or ghost display options, so you can see a faint line, so you know there's something there, but it's kind of defocused. Model collaboration. So export and imports work fine with SysML 2 models, component sharing, web interface. All of the standard add-ins that we have in Modeler work fine. Product traceability, I mentioned that we have OSLC capabilities. So that means that we can connect to Codebeamer from a SysML 2 model or any of our tools listed on the graphic on the slide, create OSLC links in Modeler from SysML 2 elements to requirements in external systems. So straight from day one, we've got digital product traceability from SysML 2 designs to market-leading requirements management tools, which is fantastic. And going the other way, our OSLC server exposes and serves up SysML 2 models. So again, from day one, other systems can access SysML 2 models through OSLC and create OSLC relationships to SysML 2 model elements. So that's fantastic. We want to be able to ensure that we can provide that connectivity with our other design engineering tools from PTC and third party as well. Here's a demonstration. This is a slightly old movie, unfortunately, with an earlier iteration of our solution. But we're in our OSLC browser. I'm connected to Codebeamer. I'm going to run a quick search. It's going to return a requirement called fuel efficiency from Codebeamer. This is live data. You know, I'm connected live to a Codebeamer instance and it's serving that up live. Here's the preview, that requirement. And I can then drag and drop onto my SysML 2 model. create a new OSLC link, call this a dependency, and there we can see the OSLC link created in Modeler, and we can review the preview and manage that link going forward. Okay. I mentioned at the start that there's an expectation for OSLC to provide a REST and an OSLC 3 API. We have Windchill Modeler 10 has a REST service and an OSLC 2 service. It actually has some OSLC 3 capabilities as well. But at this point, it's not fully compliant with OSLC 3.0. So that's another project that we have planned for the future. Here's our updated web interface with our lovely PTC color scheme. And here we see some of the SysML 2 model data through the web interface, requirements, use cases. Let's see properties and relationships on the right there. Here's our system structure diagram. Here's a text diagram. And here's our variability as well. Okay, so we're nearly done. I mentioned briefly that we have a model importer tool, but it's not quite ready for release. So into the future, we will provide this capability, we expect. But we're using it in the background, and it's helping us to validate our solution against all of the example files. The standard provides lots of example models, so we're using those to validate our solution. And here's, just for reference, provided the icons that we've implemented for the new types. I think it's something like 35, 40 new elements this release, and a few more coming the next release. Okay, so that takes us to the end of the presentation. And before I open it up for Q&A, I just wanted to thank everyone for attending.